It's 2 a.m., April 2nd, just a couple of weeks ago as of recording this. I'm lying in my bed and my whole house starts shaking. Things are falling off the shelves, and I'm thinking, oh my goodness, this is the big one. Thank goodness it was not, but I had to get an earthquake scientist on Science Solutions Santa Cruz as soon as I could. That's why I reached out to Distinguished Professor of Earth and Planetary Sciences, Emily Brodsky, who joins me on the program today. We talk about geothermal dynamics and fracking and these chain link reactions and how earthquakes work and how she measures them. We compare the 1906 earthquake to the 1989 earthquake to the one that just happened a few weeks ago. It was an amazing conversation. The 6-year-old in me was absolutely delighted. I hope you enjoy it too. So let's get right into it. I'm Jonathan Hicken. Enjoy. I'm in the studio today with Emily Brodsky, Distinguished Professor of Earth and Planetary Sciences at UC Santa Cruz. It's so nice to meet you, Emily.
Nice to meet you too.
So, April 2nd, today is April 23rd, so this is about 2 weeks ago. It's 2 a.m. An earthquake, 4.6, I think, hits Santa Cruz or hits Boulder Creek. What is the first thing going through your head in that moment?
Ooh, that's an earthquake.
Yeah, were you kind of excited?
Oh, yeah.
I live on the west side, and I could kind of feel to me, it felt like a wave. Mm-hmm. Where you live, were you able to kind of feel that?
I also live on the west side, kind of near Bay and Mission. And, yep, definitely felt it. And I live in a 2-story wood frame, and so it shakes. Yeah, no, that one rolled for a while. I was actually surprised at how small it ended up being in the end.
I had the same, I was laying in bed, and I was like, oh, here we go. It's coming. Especially when that big wave, the first, more intense wave rolled through. I was like, okay, we made it. It's happening. So at what point did your sort of excitement about feeling this earthquake stop and your scientific mind kick in? And you're like, what can we learn from this?
Oh, 2 to 3 seconds.
Okay, yeah.
It doesn't take long.
And so what were some of the questions coming up in your head in that moment?
Well, first of all, I thought it was going to be bigger than it turned out to be. And I'm like, well, and so where was it? What its relationship is to the San Andreas cycle. Are we going to get aftershocks? And what comes next? It's always what comes next, right?
The San Andreas cycle, what is that?
Well, the last really large earthquake on the northern San Andreas was 1906. And after a lot of aftershocks from 1906, the system kind of quieted down in the north and has been very quiet for quite some time. If you compare 20th century seismicity or 20th century rate of earthquakes to the 19th century, there was a lot more going on Hayward, Calaveras, San Andreas in the north than after 1906. And so at some point, it's got to start waking up again.
1906, of course, is we kind of think of it as the big San Francisco earthquake.
That's correct. Earthquakes actually span some distance. They're not just like dots on a map. And so the 1906 earthquake starts sort of mid-peninsula, and it ripped all the way down here kind of to basically Watsonville, San Juan Bautista area, and all the way up to Mendocino County. That's all one earthquake.
And when you're defining these bounds, how are you defining those bounds?
That is the fault slipping. Okay. So the fault slipped on the fault plane over a few hundred kilometers.
Okay, so the entire, I understand faults to be like plates, right? Tectonic plates, is that right?
Well, sort of, okay. Plates come together on seams, and those are faults. And most plate boundaries don't just have one fault, but, a few faults that help accommodate the plate motion.
I see, okay.
Okay. And the San Andreas does a lot of the plate motion between North America and the Pacific, but not all of it. It gets some help from its friends.
Okay, like you mentioned the Hayward-Calaveras fault, for example.
Like the Hayward, like the Calaveras, like the San Gregorio, like a whole bunch, which is offshore.
So in 1906, when that earthquake happened, it was actually a whole, like, hundreds of miles of span that the whole piece slipped.
Yes. So, most of the time the plates are moving. So if my elbows are like the Pacific in North America, and most of the time the faults are not moving. So you've driven over the San Andreas 100 times. It's anytime you drive over the hill over Highway 17 by the reservoir, you're driving over the San Andreas fault. And most of the time you don't notice it being there at all. It's not moving. You just drive over it. But when the plates are moving all the time and the fault's not moving, every once in a while, the fault has to catch up.
Oh, interesting.
And so it's that catch up that's the earthquake.
So help me understand, because I think of a seam as like an absence of matter, or an absence of land. But in this case, it sounds like the fault is actually, what is a fault made of, I guess?
Rock.
Okay, and how is it different from the rest of the plate?
I need props. I wasn't thinking when I came down here. Do you have a couple of books or bricks? Or
Yeah.
something?
Let me grab. Edith, I'm gonna go grab some books. I'll be right back.
Okay.
All right.
So you keep asking me what a fault is.
Yes.
And I sent you running out of the room to get me some toys. So thank you very much for the toys.
You're welcome.
Okay, imagine we've got two sides of a fault here, these two lovely green blocks. One of them is Santa Cruz and the other is San Jose. Okay, we have the San Andreas between us. And if you imagine that my hands are the plate motion, North America on the San Jose side, the Pacific on the Santa Cruz side, and they're always moving. But most of the time, the fault is not moving, and this is where the blocks aren't a perfect model of the Earth. The Earth ends up sort of twisting and deforming to keep up with the plate motion, but the faults there's a lot of friction between them, and so they don't get to move. But every once in a while, they slide to catch up.
Got it.
Okay? And so when I say there's an earthquake from Watsonville to Mendocino County, I mean that the fault was sliding on a line or all the way over that distance.
Got it. Understood. And and then I'm also assuming then that these aren't like perfectly firm pieces of block like you're just demonstrating, but maybe there's some sort of fluidity to it also that, that would make it so that only a section moves at a time.
Yeah. The Earth is a little squishy.
Okay.
And so the northern San Andreas all slipped in 1906. The southern San Andreas from about Paso down through the Inland Empire east of LA all moved in 1857. And in between Paso and San Juan Bautista is kind of a fun section of the San Andreas, which is moving all the time. We call it the creeping section. And that part is not locked in between earthquakes. It actually just keeps up with the plate motion and therefore doesn't generally have as big earthquakes because it just is releasing all of its strain as it goes.
So does that mean just like more frequent, smaller earthquakes?
Or just gradually sliding.
Okay. We may not even detect it.
Yeah, right. It just kind of goes with it.
So you know so much about these earthquakes that have happened throughout California and I imagine the world, but how do you actually measure these things? How do you actually study them?
How do I study earthquakes?
Yeah.
Well, lots of different ways. Sometimes I look at seismograms. Seismometers measure the shaking, the ground motion from the earthquakes that, the ground motion that wakes us up at night. And you can take a close look at that motion and you can piece out how the fault slipped. Sometimes I look at them a little bit like a statistician, that I think a lot about how one earthquake triggers another earthquake, triggers another earthquake, triggers another earthquake, and what that kind of chain reaction looks like. And I do that by taking the seismograms and doing a little bit of machine learning, a little bit of AI these days, and working out what patterns are in the data. I also sometimes think about the friction on faults. Friction is what holds the faults in place in between earthquakes, and you have to overcome it to have an earthquake. It's also sort of the brakes on the process. And so I study friction by going out and looking at rocks and trying to sort of forensically figure out what their friction had been during motion. A couple times, I took a fault's temperature, which may not be the most obvious way to study an earthquake, but if you think about it, when you rub your hands together, they get warm. If you stop rubbing and you stuck a thermometer in them and you knew how many times you went back and forth, you could actually figure out what the friction was between your hands. And so you could kind of backtrack to the friction of the faults this way.
So you can measure the temperature of the earth, and these faults. How do you actually do that?
You drill a big hole.
Like, how deep are we talking?
So after the Tohoku earthquake in 2011 in Japan, that was a magnitude 9 earthquake, we took a drill ship out and under 7 kilometers of water and drilled a hole to 830 meters depth beneath the sea floor and found the fault and stuck some thermometers on it.
Oh my gosh. So you really reached into the earth almost 5 miles down, including the water and
including the water.
Yeah.
Right.
What did you measure in that particular case? By the way, that's the earthquake that I think sent a tsunami across the Pacific and did some damage here, right?
A little bit of damage here, and it was, a lot of people remember 2011 for the big tsunami in Japan and the Fukushima disaster.
That's right. And I seem to recall there being some impacts of the tsunami in the Santa Cruz harbor, and it maybe caused a little damage in the harbor.
I believe so.
Yeah, that's right. Okay, so what did you learn on that field research excursion?
Well, by taking its temperature, we realized that the temperature was much smaller than you might expect for these giant plates sliding past each other 70 meters. So in that one earthquake, it was one side of the fault slid past the other by 70 meters.
Okay.
And
that's a lot of distance.
It's a lot of distance, right? It's pretty close to a football field.
Oof, okay.
You would have thought if you did that, you would end up, practically melting the rocks, right? It's really hot. But in fact, at least by the time we got there a year later, it was 1/3 of a degree temperature elevation over the fault. And so that teeny tiny temperature rise means that the plate boundary had to be pretty weak, that it didn't have very much breaks, which might be why it had such a giant earthquake. There were no brakes on the process.
So no brakes, like you're using that word almost like a car brake.
Yeah.
Yeah. Okay. So it was loose and it just slipped.
Yeah.
And so it wasn't rubbing super, super hard.
Yep.
Interesting. So were you able to derive any sort of insights from that, or was this sort of like a one-time?
Well, I think that was a pretty fundamental insight in itself, that the fault was much weaker than most previous laboratory experiments or analysis would have suggested.
I see.
And that sort of changed the paradigm of how we think about the resistance to motion on faults. So that was very much a sort of first principles, kind of fundamental, like, how does this thing move kind of project. Whereas other things that I do sometimes, like the statistics of how one triggers another, are more empirical, and maybe a little bit more directly related to the question that everybody always wants to ask, which is, when's the big one coming? Something else I do is sometimes look at human-induced seismicity. That is, anytime people shove water or other fluids in or out of the ground, when you pull oil out or you push water down, you change the forces on the faults. And that too can trigger earthquakes.
So why would we as people be forcing water or oil into the earth?
Oh, We take oil out of the earth.
Okay, that's an example.
That is an example.
Okay, fair enough.
Also, fracking.
Fracking.
Okay.
That's a term that I've certainly heard plenty, but I'm not sure I totally understand what it is and what the purpose of it is.
The purpose of fracking is to be able to pull natural gas out of the ground.
Okay.
And usually natural gas is in really, really tight pores. It's really trapped in the rock. And so the idea of fracking is you put high pressure water in and you open up the system. You make fractures. It's short for fracturing.
Okay.
And then the gas is able to flow out.
And then we grab it.
We grab it.
Yeah,
You
okay.
got it.
Got it.
All right. So geothermal energy is another big reason you might want to put fluids in or out of the ground. You pump steam out, you run a turbine, you generate electricity. When the water gets cold after been running around a little bit, you shove it back in. And that too changes the forces on the faults. And so many geothermal plants also make earthquakes.
Okay, so geothermal plants make earthquakes. That means humans can cause earthquakes.
Yes.
Is I think what I'm hearing. And
Yes.
that's a definitive yes.
Oh, yeah.
Oh, interesting. Okay, so what?
That's not controversial.
That's not controversial. So what does that actually, walk us through the sort of the physics of that? How is the pressure that we're adding to the system causing these earthquakes?
So we get earthquakes, as I started to say before, when the force pulling on the fault overcomes the friction.
Mm-hmm.
That's when we get earthquakes. Friction is what keeps the fault closed, and when plate motion gets over it, off you go. And so anything that either changes those forces or changes the friction will make an earthquake. So you get a choice.
Okay.
Okay. So if you pump water directly into a fault, then it's sort of like a hydraulic jack. It kind of pushes apart the sides of the fault and it makes it easier for it to move.
Uh-huh.
Okay. So that and basically reduces the friction and off you go. Or that water can push on the rocks around it and those rocks might push on some other fault further away. And that sort of chain reaction there could cause that fault to be more loaded and off it goes. So both things happen.
I see. So let me try to repeat this back to you.
All right, please do.
So, okay, in one case, we add the water into the system or into the fault, and it kind of like, the way I think about it is it almost kind of separates the plate a little bit, which reduces the friction and allows it to go. In other cases, we're adding pressure to the system. This fault's not moving, but it's kind of pushing that plate that way, and it's adding pressure on the fault on that side, and then that adds enough pressure that one goes.
You got it.
Okay, boom, I'm with you.
I like the hand signals. The hand signals, those worked.
For those of you who are listening to this episode, you should watch it because we're doing a lot of hand gesturing here.
Yeah, we talk with our hands.
We
here.
sure do. Okay, and so I mean, fracking in the sort of the environmental field is just we immediately assume it's bad for the environment, and I'm hearing it has also the potential of causing, or it not the potential, it does cause earthquakes.
It can. The more common way that fracking produces earthquakes, we're really good at making earthquakes. We have a lot of different choices, is because of the environmental consequences of fracking, that you have those chemically nasty fluids down there. Usually what most companies will do is suck back those fluids, and then they have to get rid of them somewhere. And, out of sight, out of mind. An extremely common solution is to take all that wastewater and just shove it as deep as you can into the ground.
Oh my gosh. So it's just like mega super fracking. Or it's like even doing what they were doing before, but even deeper.
Yeah, but maybe you do it in a piece of rock that might have some holes in it already, so it might be a little easier to get into. People sometimes use abandoned old oil fields thinking that, something came out of it. We got some room down there. Let's drop something else in. And, it's not a totally stupid idea. I mean, it's better than dropping it in the ocean, right?
Sure.
Right? I mean, it's not dumb. But if you keep doing it and keep doing it and keep doing it, you can eventually build up some pressure down there.
Okay. And that would, of course, then cause more earthquakes.
Yeah. And, I mean, let's be realistic, all right? A magnitude 2 or 3 earthquake is not the end of the world, right?
No.
And so, for instance, geothermal is otherwise a reasonably sustainable energy source. And we're sitting here in your lovely studio with all your electronic equipment and your lights, and we like electricity, right?
We sure do. Yeah. There's no doubt about that.
And so we got to get it from somewhere. And if the cost of having electricity is a bunch of magnitude 2s and 3s, I'll take it over global warming any day.
Well, yeah, we can live with that.
Right, exactly.
In fact, I think about friends or people who aren't from California who come out here and they feel their first little earthquake. It's almost like, ooh, that was kind of fun.
I just told you I was excited. So I think the problem is that you do need to be a little bit careful about where you choose to do geothermal. Pumping fluids in and out of the San Andreas, where you're not sure if it's going to be a magnitude 3 or 7, may not be the smartest move. And I will tell you there are major geothermal projects on both the northern and southern end of the San Andreas Fault.
Oh, so we're getting it from both sides.
Oh, yeah.
Okay.
The geysers and the Salton Sea.
Okay, yeah, sure. That's the whole stretch.
If you haven't visited the Seymour Marine Discovery Center at UC Santa Cruz in a while, or ever, you really should come visit us. We are right on the bluffs of the beautiful Monterey Bay, with an aquarium full of local species and a bunch of hands-on science exhibits that help you understand what's happening in our ocean and along our coast. We are connecting the incredible research happening at UC Santa Cruz with real-world solutions for our coastal community. We don't want science to just sit on a shelf. We want it to shape decisions, inspire kids, and help our community feel equipped to act. So if you care about the future of our ocean and our coastal community, or you just want to experience a place that makes you feel a little more connected to it, come visit us at the Seymour Marine Discovery Center. Science Solutions, Santa Cruz.
Are you involved in these discussions? I don't know if it's at a policy level or whatever, of like raising the awareness of the implications of this work?
I am involved as a scientist.
Yeah.
And when people ask me my scientific opinion, I always give it to them.
Yeah.
Sometimes it's something they want to hear. Sometimes it's not. That's not my business. My business is to give their scientific opinion.
Is the government, the California government, or these companies, are they inviting you to come share that opinion?
At various times, various companies have invited that opinion.
Okay.
I think at this point in time, it's well enough understood that geothermal makes induced seismicity. They don't need to hear it again.
Yeah.
They just need to make their decisions.
Going back to, you were discussing the sort of I kind of think of it as like a chain link of studying, and maybe this is how you're deploying AI or machine learning and understanding, this series of earthquakes and how one might trigger another.
Mm-hmm.
Can you tell us a little bit more about what that is and what you've learned about this sort of this chain link reaction that you've observed?
One thing we've learned is that seismic waves can make that chain reaction. So if you shake a fault, that can shake it loose a little bit and make another earthquake. And that's interesting for a number of reasons, one of which is that seismic waves for big earthquakes can be measured around the world. When that big Tohoku earthquake happened, we can see it on seismometers here in Santa Cruz. That means that those seismic waves are potential triggerers everywhere. And so you could get these very, very long range connections between earthquakes.
And that an earthquake that happened practically on the other side of the planet is registering here, and that we're able to connect it to other seismic activity in our area?
Yes.
Okay.
So that in general, when we do these sorts of studies, you do statistics of populations, not individuals. And so the earthquake rate can increase. There's always earthquakes in California, right? There's always earthquakes. But the number of earthquakes per day could increase due to some waves coming in from Japan. Another interesting thing we found is that the bigger the waves, the more the rate of earthquakes increase.
The bigger the seismic wave.
Yes. If one earthquake's either really close or really big, it makes big waves, then that's much more likely to trigger more earthquakes than a small one.
Have you been able to detect any patterns and that might, I know that predictability is like the hot thing everybody wants to know about, but have you derived any insights from this chain reaction that help us understand what's going to happen next?
Two things. One is what I just told you, that earthquakes can trigger another. If you measure that probability of triggering another, that in and of itself is a prediction. It might not be a very societally useful prediction because usually what we see is you hit the ground with like a centimeter per second. Maybe you double the earthquake rate. So you went from 1 magnitude 3 every year to 1 magnitude 3 every 6 months. It's not societally that interesting.
Because a magnitude 3 is just not that big of a deal.
Yes. Now, there's a couple of footnotes there. Number one is the way earthquakes work is there's a relationship between how many magnitude 3s you get and how many magnitude 6s you get.
Ooh, say more.
Okay. So in general, on the planet, you get 10 times as many magnitude 3s as magnitude 4s, and 10 times as many magnitude 4s as magnitude 5s, and 10 times as many 5s as 6s. It's called a Gutenberg-Richter relationship, named after Bino Gutenberg and Charlie Richter.
Okay, and so the Richter scale is the sort of tenfold measurement.
Well, the Richter scale is how to measure the magnitudes.
Okay, got it.
But once you've measured the magnitudes, there is also this relationship between how many earthquakes you get of different magnitudes.
Okay, fascinating. Got it.
Okay. So, for instance, in general, here in California, we're able to measure most things a little bit under magnitude 2 and bigger, but we think that keeps going. There are 10 times as many 1s as 2s and 10 times as many magnitude 0s as 1s. And so there are earthquakes all the time. Okay.
There could be one happening right now, and we just don't detect it.
There is one happening right now. Okay. And I think of the little ones as sort of the fruit flies of seismology, right? That they're happening all the time. They give you lots of good statistics, because, you could go through lots of generations of them, and it's a ton of information about the signal. But it took biologists a while to figure out fruit flies were the way to go, as opposed to the charismatic megafauna. And it took us a while to realize little earthquakes are the way to go. And that's certainly something in recent years we've become much better at measuring by having denser seismic networks and better detection methods. And this is another place machine learning is helpful in improving our ability to detect earthquakes. And now we have fruit flies. And now I can routinely work with million earthquake catalogs where I can look at the interaction of those million earthquakes, and there's a lot of richness to that pattern.
Of course, because when you have more data points,
yes,
there's more to learn there, right? This is something that we learn in statistics, right?
Yeah.
It's a higher sample size, right? That's the idea.
We like big sample sizes.
Okay, and so you're getting you being you personally, but also the field has recently got better at measuring these little earthquakes. What have we learned since being able to do that maybe we were missing when we were only looking at the big ones?
What we've learned, for instance, is these triggering patterns.
Okay.
Those are primarily seen on little earthquakes, and there just weren't the statistics there when we were only detecting big ones. By looking at the little earthquakes, we can, as I say, do this sort of weak form of prediction. Say, well, hey, I see, seismic waves coming here from Japan. I bet there's going to be a rate increase in California. We can actually quantify that and show what we expect. Even if it's not actually that exciting, a rate increase, we can do it. So that's something. We also have found that specifically in Southern California, that the number triggered by seismic waves is proportional to the size of the wave. So if you double the size of the waves, you double the number of earthquakes triggered. If the waves coming in from Japan increase by a factor of 10, the number of earthquakes triggered by a factor of 10. And that's a really interesting observation because it tells us something about how many faults are that close to failing. How does that population work? And what that observation means is there are some faults that are sitting there this much a hairbreadth from having an earthquake. And there's some faults that are further, and some faults you need to slam them pretty hard. But actually, when you actually run through the numbers, there are just as many faults that are, we measure these things in pascals, 1,000 pascals from failure as there are from 1 pascal from failure, that the faults are sort of spread out with some of them just ready to go and some of them very, very far in their cycles. And when you take the group of all the faults in Southern California together, they're sort of evenly spread out over their cycles. And that gets interesting because you could have imagined a world where they all got synchronized, right? Where they all kind of were running in lockstep. Some people like to call this the decade of terror scenario, right? Where you have one earthquake and it makes another and every single fault in California goes at once. But actually, at least for Southern California, they're kind of spread out. And so you'll get one and it'll have some aftershocks. But then there's no particular reason it should trigger everything. And now there are other places in the world, like the very bottom of the lock section in Cascade in the Pacific Northwest. We call it Cascadia. Or southern Japan, where the system is pretty synchronized and all the faults are kind of doing the same thing. And so by looking at these triggering signals and doing the statistics and these million earthquake catalogs, we start to realize that different parts of the planet are behaving differently on how their faults interact.
How cool. So, I mean, I'm like picturing the Earth in my mind, and certain areas are like kind of chilling, they're good, no problem. Other areas are lighting up and getting big earthquakes. And I imagine it's those little spaces are constantly shifting and moving around the planet. Would that be a fair way to sort of picture it?
Sure. But the interesting thing is there's some organization there. Some fault systems choose to spread themselves out and everybody marching to their own drummer. And other fault systems are a little bit more militaristic and kind of going all together. And so that's the question. Why does this one do that and the other one do the other thing? And so that's part of what we're trying to figure out.
In your work, how far back in time do you look? Like, has the Earth always behaved this way?
Depends on what I'm doing. If I'm doing earthquake statistics, it's rare for me to go back before the digital era.
Okay, sure. Because that's when all the data becomes available.
The fruit flies are better in the digital era.
Yeah.
You know, sometimes I'm interested in big earthquakes and I could go back further, you know, based on historical records. Or I do sometimes do volcanoes, and volcanoes are a little bit more rare in their eruptive cycles. And so you have to go back in historical to the non-instrumental era. You know, if I'm looking at rocks, it could go way back, right? If I'm trying.
Sure.
So it kind of depends on the question that I'm asking that day. I should also point out, I was giving you the long list of ways we study earthquakes. Another way that's not obvious, I think, to people who don't do this for a living, is we have a lab, like an experimental lab.
Cool.
And what we do in that lab is we try to simulate and isolate different processes that are involved in making an earthquake. So for instance, a researcher who works with me, Will Steinhardt, has an experiment he likes to call Squishy Slidey. It's kind of its pet name. You spend enough time with your experiment, you start giving it pet names. And when you start talking to it, we worry. But Squishy Slidey is fantastic. It's like made out of transparent rubber. And so it's like the San Andreas or any other fault, but scaled way down and much softer, so that parts of it can slide while other parts stay stuck. And we can make a whole movie of the sequence of events, and we can figure out how that sequence evolves naturally, how the history of where slipped when leads to the next set of slip events.
So you've constructed a whole experimental model essentially that you can go and trigger earthquakes right here at your lab at UCSC?
Will has constructed a whole experimental setup.
Shout out Will. Shout out Will.
Will occasionally, lets me turn the light switch on. But
how cool is that? So are you actually, and then do you experiment with the sort of the fracking scenario? Or are you injecting water into these systems?
That one's a dry experiment. Okay. And there's enough to do in the dry experiment that we find it interesting.
Yeah, one thing at a time.
One thing at a time. And so what Will has been doing is sort of reproducing a lot of the basic observations we have about earthquakes. How much slip on average do they have in an individual event of a given size? And do they lock up before they slip? The answer is yes, they do. And can you, based on the locking pattern, predict the slip pattern? Yes, you can. How does the whole state of the fault sort of self-organize itself? Does it spread itself out over all those cycles, or does it want to synchronize? Those sorts of questions we can ask on this system.
When you say lock up, that means it gets super still right before it moves?
Yes, that if the sides, sometimes you have the sides just sort of gradually slipping past each other, then they get a little stuck right before it goes.
Got it.
And then we have some other experiments. We have lots of fun experiments. You should come visit sometime.
I would love to. I would absolutely love to.
You're invited. Come on up.
Thank you. Can I bring my 6-year-old and yeah.
Sure.
Well, Emily, let's bring this back to Santa Cruz for a little bit.
Okay, yeah.
So many listeners will remember the 1989 earthquake.
Yeah.
I believe neither of us lived here at that time.
That's correct.
Yeah, I certainly didn't. I was 3 years old and I lived in New York.
Okay. Whereabouts?
Austining.
I grew up in Mount Kisco.
No kidding. I was a 3-year-old gallivanting around in Austining, New York in 1989.
All right. We grew up, for those of you listening, we grew up 10 minutes from each other.
That's incredible. So we weren't here, but many listeners do remember that. Mm-hmm. What was different about that earthquake, or that you know of, and maybe the one that just happened a few weeks ago, and maybe the one that happened in 1906? What were some kind of differences that we might find surprising?
Well, Loma Prieta was a surprising earthquake because it was on the San Andreas, or extremely close to it, yet it moved in a direction that you wouldn't necessarily expect for the San Andreas. The San Andreas is predominantly a strike slip fault. That is, it is slips horizontally in the that way.
Okay.
In the direction of Los Angeles becoming a suburb of San Francisco.
Right. So it's almost like you can imagine like a north-south slip, kind of like that.
Right.
Okay.
Whereas Loma Prieta in 1989 slipped with a big component vertically.
So it jumped up.
Yep.
Okay. And that is usually when a plate kind of slips underneath another one. Is that?
Yes.
Okay.
A block of earth slipping underneath another one.
Okay.
And so that was a bit of a surprise because that's not the way the San Andreas is supposed to move.
Right.
Somebody forgot to tell it. Interestingly, that earthquake we had at the beginning of April, just to come back to it, was a very similar sense of motion to Loma Prieta. It was further west. So it wasn't the same fault. In fact, it's a little confusing what fault it was. But it was also that sort of thrusting motion that is not quite what you would expect in this region necessarily.
What do you think's going on?
I don't know. That's what keeps it interesting.
Okay, and would this be unusual, though, broadly speaking, that one fault might exhibit these unusual behaviors from time to time?
Yes, the Earth keeps surprising us.
Yeah, sure.
Right.
I bet.
It's not quite so simple, which is what makes this an interesting thing to study.
How does it feel for you personally to be like the person in Santa Cruz that everybody goes to understand what happens when an earthquake happens?
Oh, well, there are other people.
In that case, to be one of the people, I mean, I imagine the press was knocking at your door and you're here on this show. Your friends are probably wondering what happened. How does that, is that a weight for you to kind of?
I don't mind very much.
Okay.
It's, it's nice to study something that other people can appreciate and understand what you're doing. And I'm an academic scientist. I work for the University of California. I don't have the same kind of responsibility to provide public information in real time as my colleagues do at the U.S. Geological Survey, where when an earthquake happens in the middle of the night, they need to jump out of bed and get on a television camera. I jumped out of bed and started slacking all of my students and colleagues, and we were all up all night, having a nice conversation about it. And then, in the morning when somebody wants to hear about it on the news, I'm happy to talk to them. So it's a very different kind of relationship with the public. And that's, I'm happy to share.
I mentioned a minute ago, I have a 6-year-old. He goes to Bayview Elementary. And, I think he's going to be absolutely thrilled that I got to talk to an earthquake scientist today. I remember being that age and being fascinated with earthquakes and volcanoes and all of these things. When was it for you that you realized that this was something that you wanted to dedicate your life to?
Oh, about my 3rd or 4th year of grad school.
Oh, okay. That's...
I was a late bloomer.
So what were you studying before and how did you get here?
Interesting question. I was studying geophysics and geology in grad school, so it wasn't like it was that far away. But I went to grad school saying I would do anything other than seismology. And, as us parents know, when a kid says something like that, there's something else that's about to happen, and so my advisor was very skilled, and Hiro Kanamori, and he didn't tell me I was studying being a seismologist. He said, of course not. You're not doing seismology. But, let me talk to you about this fun earthquake that just happened. And, and I wanted to study volcanoes. And so he found earthquakes on volcanoes. And then suddenly I wasn't talking about the volcano. I was talking about the earthquake. And, one thing led to another.
And you woke up one morning, you're like, I guess I'm an earthquake scientist.
Kind of, yes.
Well, before we wrap up, Emily, one question for you, and then if there's anything else you want to share or plug, what is something that we being those of us who don't live and breathe earthquakes every day, what is something that you think we get wrong or that we misunderstand about earthquakes that you want to correct right now?
If we knew when the big one was happening, we would tell you. It would not be some secret.
There's not some big conspiracy to conceal the prediction.
I would be extremely happy to share that information.
All right. That's really good to know. That's good to know. Thank you. Anything else that you want to share or you want to get out before we wrap up for the day?
I think, no, this was fun.
All right. Well, thank you so much for being here, Emily.
All right. You take care.
All right, that does it for the pod today. That was an amazing conversation. I geeked out on earthquakes. I hope you did too. Thank you, Emily Brodsky, for coming on the show today. Thank you, Edith, for editing, Cassidy for production, Valerie for distribution and socials. And again, please do like, subscribe, follow, comment, rate, engage in general. It really does help the show get in front of more people in our community who might be interested in this stuff. Until next time.